Hi, we are the group number 4 and we will expose you our project about the design of a centrifugal pump.
To start with this presentation, I will make a brief explanation of the importance of the pump. A pump is a piece of equipment that consists of a set of rotating blades enclosed with a casing that by their rotation imparts kinetic energy to the fluid, which results in an increase of pressure. Given its importance in the industry, it is important to model and analyze the behavior and performance of the pumps as chemical engineers under a variety of operating conditions. So for our project, we use the Coolidge nomenclature, so this is an important information you should know. The objective of our project is design and characterize a centrifugal pump by the CFD approach in order to understand and compare the developed metals with the model by Graham-Voss. So yeah.
Okay, about the literature review, we use the article of Valdez from 2020. We have here the title, and this article was important because it helped us to compare and establish optimal range. And also, the article exposed the importance of the CFD in the design of the pumps because construct a pump is very expensive. So the CFD is very important is in this file of the industry.
In order to understand this project, we have a specific procedure. This starts with the design of the pump in Microsoft Excel. Later, we have the physical design in Inventor Dex 2021, and we finally have the run of the mesh and the simulation of different processes with oil and water. And those are done in Star CCM+. The methodology is divided in three parts: mesh assumption, source of results, and geometry pump.
For the volumetric meshing, a polyhedral mesh was selected given the complex geometry of the pump. A prismatic layer measure was selected to be able to describe the behavior of the fluid in areas such as the walls. With the same parameters, initial meshing conditions were taken from the volume page, finding the data size of 0.025 meters. For independencies, we additionally mesh with a base size of 0.0325 and 0.0775 to obtain the values of total server CPU time, efficiency, and total head, which are presented in the independence meshing table. From this, it is chosen that the mesh of best convenience is that of 0.025 meters.
In the second part of the methodology, we have the source of results. We part from these data that are the density, viscosity, and operation temperature of water and oil. And with this, we can do the design of the pump.
Now, in the geometry, we use some equations to create the volute and impeller to create all the pump. And these equations was taken from some methods, the method of hydraulic pump design and the method of speed triangles. The equations of these two methods are very useful because it can help us to calculate some important parameters like efficiency, head, total pressure, torque, and more else. Now we talk about the geometry. We use the app Inventor 2021 to create the parts and the assemble. Here you can see the parts that are the impeller and the volute, and the assemble of these parts that you can see. And this assemble is the complete pump.
For the result, we have two fluids, water and oil. For the first part of the result, we have the simulation data that varies with the volumetric flow. We just change this volumetric flow and simulate again and again until we have all of these stable results. Now we present the results of the impeller velocity with 0, 25, and 182 meters at 3 per hours. And we have a range from 0.1 to 49.4 meters per second. Now we have the impeller velocity for 210 and 228. Now we have the result of the cavitation seen in every volumetric flow.
So here we can see the volumetric flow of the cavitation at volumetric flow of 210. We can see that is in a range of in the middle. So we can say that it is a good flow and a good condition. So here in the BEP cavitation, we use a different type of diagram, so we can show you where is the cavitation really happening. So we can see that the cavitation, it's really just in the middle, in the center of the pump. So it's really not that bad, and it's really a good flow. So it doesn't cavitate with the pump. With the pump.
Now we have the result of the vector leasing in every volumetric flow.
So for the vectorial velocity for the volumetric flow of 210, we can see that it's in a range in the middle. So we can say that it is a really good volumetric flow, that it's really going in the direction it should be, and it's happening in a really good state. It doesn't really cavitate. So for the vectorial velocity for the BEP, we can see that it is really it's in the range, it's in the middle range, so we can say that it is a really good flow, because it's not that red or it's not that blue. It's really just in the middle, and it's just like the a good yeah, range for it to have.
Now we have the Wall-J plus scenes that are presented in all of the volumetric flows, but specifically in the five principles that we said at the beginning. And now we're going to explain why these colors, or what is the meaning of these colors.
So here we can see the Y plus of the impeller. We can see it is in a range in the mostly below the medium range, more or less. So we can say it is a really good wall Y plus. So here we have the wall Y plus for the BEP. We found the range really low, but it's what we had.
And now here we have a table with the results of the oil simulation data. And as you can see, we do 7 simulations in this case. And yeah, here is the table with the volumetric flow, mass flow, and the parameters that we obtain in STAR. And now here we have the simulation data of the BEP. We calculate the BEP based on a graph of efficiency versus flow rate. We obtain the equation that represents the graph. We derive the equation and equal to 0. And finally, we obtain the flow rate for the BEP. Here we have the impeller velocity for flow rates of 0, 90, and 182. And here we have the rest of the flow rates. As we can see, the impeller have the expected behavior. In the center, we have low velocity, and in the borders, we have high velocity.
From the cavitation picture, we can see that there is a constant pressure in the impeller at different flow rates. We cannot conclude whether the pump cavitates or not because we do not have the oil vapor pressure at these conditions.
Now, here we have the scenes of the vectorial velocity, the flow rates that you can see in the slide. Here we have the rest of the scenes, and we can see that the pump have a backflush zones. These zones could be generated by experimental errors or modeling errors in the application of a star. Finally, we have the results of worldwide plus, and you can see the image of the worldwide plus for different flow rates. Here we have the rest of the scenes of worldwide plus for all the flow rates, and we can see that the worldwide plus is a very good result because the value of this parameter is less than 1. And now you can see the animation of the velocity, vectorial velocity of the BEP flow rate. And finally, we have the animation of streamlines. And here you can see very well the backflush zones that we present in previous results.
Now for the results, in this part, we used the Valdez article, and we presented the volumetric flow versus efficiency and the volumetric flow versus total head. We have the orange color, that is the water, the gray color, that is oil, and the blue color, that is the fabricant. Finally, in the conclusions, we can say that the efficiency of the water was higher than the efficiency of the fabricant, but this doesn't mean that the fabricant pump is better than ours. As we can say, the fabricant pump is the better one because we did have some mistakes during the simulations.